Welcome back. This has been a delightful adventure in trying to think through the broad reach of this idea of patterning as a result of both positional information and Turing. And, to confess honestly, I feel pretty motivated to keep going. And I likely will add a few more vignettes in another few weeks just because it's been so interesting to see the many beautiful things that people have done. And I told you earlier that I wanted to be a lover, not a hater. That I wanted to celebrate the achievements. I spoke about two versions of a sense of wonder. So with respect to science and not taking things for granted. And so one of those was the splendor of nature. And of course, I'm never going to bend on that. I just look out the window and you feel it. Even if you're in a neighborhood, which I am right this moment, I can look out the window and see this beautiful, interesting tree, which is a landmark on our street, and it's a pine tree, and it's amazing, honestly. But the second point was to celebrate the wonder of the ability of the human mind to penetrate the void, to learn things about the natural world that are solid, and to continue with my theme of frustration, I guess, and for which I should probably apologize, but just incredibly frustrating to live in a world where I'm thinking of a moment in 2000 where a friend of mine had one of the earliest GPSs. It was a gadget that, was expensive back then. And he and I were deep in the mountains in a region called the Vercors outside of Grenoble, near a beautiful mountain called the Grand Vémont and the Montaguille, which are out on the plains of the Vercors. And we were quite a ways away from anything. And Pierre knew exactly where we had left the car, and he did that by programming its coordinates before we left. And so what we did is this was not in the era of Google Maps or something. We basically programmed in our coordinates, and then we followed his GPS device, and the GPS device took us to within a meter of where we had parked the car. We had gone super long way to climb this mountain and then come back. And what does this have to do with anything? It has to do with the fact that that's knowledge. That's real. It's not some fantasy. It's not a point of view. It's not an opinion. It's an understanding of how the world works and utilization of that understanding to get somewhere. And so, I have been trying to express this deep appreciation for when we do the hard work of knowing things. And it's super hard, in the history of science, it's just littered with examples of wrong ideas, whether it's the beautiful idea of epicycles and deference for planetary motions, or caloric as an idea for heat, or phlogiston and oxygen, or the ether, the specific heats of solids and the law of Dulong and Petit, and it just goes on and on and on. Mark, and one of my other frustrations, I guess I'm coming across too frustrated, but is the way we denigrate somebody like Lamarck as though he was an idiot, when he was far superior as a scientist to, I would guess, most of us, certainly me. I think he wrote this book, Histoire Naturelle, which you can go look at. This guy was on top of things. So anyway, I wanted to marvel at the achievements of people, and this topic of patterning is so interesting. And the two worldviews, positional information and spontaneous symmetry breaking in the form of Turing, are just really cool. So I look forward to talking more about that. So today, what I want to do is, I feel that I got really wrapped up in the calculations, and I want to try to come back to the experimental world of biology. So on the top left, there's this point of view paper by Green and Sharp, which I think is it just rocks, and I recommend that you read it. I mentioned this in the previous vignette, I think, where I was just pointing out that we like to dichotomize. I think it was in my vignette about defiance, that there was this, that for the MWC model, that we like to dichotomize the different perspectives on allostery. And the reason I brought it up in the vignette on defiance was because of vitalism. And I mentioned in the context of enzymes, that Pasteur had this point of view that enzymes were about living organisms and how they make a living, and then the Buchners had this idea about enzymes as chemistry, and there was this hostile interaction between these two points of view, but they were both right. And here, what I think, this great in Green and Sharp's article is that they try to lower the temperature by just saying, these are both great ideas and maybe they work together. And so the specific case study where they might indeed work together is the thing shown at the bottom. Here, let me move out of the way. I guess I can't really get out of the way, but you can see the abstract of this paper. And, it has to do with digits and patterning. So I'll say a few words about that. So from the Green and Sharp paper, they point out that on the right side, the positional information, French flag idea that we've already talked about, that's something that has been explored experimentally. We talked about the quote unquote failure of the French flag model, but that was too harsh because there were lots of, we intentionally simplified, and then we said, well, what are the implications, and then what would happen if we changed the gene dosage, and so on, and it was more subtle than that. But then there's additional experiments. For example, looking at the relationship not between the cephalic furrow and bicoid gradient, but between hunchback and bicoid. The story seems to hold together better. But then, I pretended that the morphogen gradient was in steady state. But people like Nauman Barkai and even Crick, in a beautiful paper, from 1970 or so, have thought about the time it takes to form a gradient. So that's all fine. On the left-hand side, Green and Sharp do this really nice job of trying to give a little bit of intuition for how the Turing mechanism works, and I just wanted to say something about that intuition because the math might have disguised that. Remember, the big idea here is that you have two diffusion coefficients and they're different. And you might ask, well, what does that have to do with the emergence of a pattern? And what they show here is, imagine a little perturbation, a little instability, or a little heterogeneity of autoactivator where there's a slight increase in autoactivator in some region, and that will build upon itself because of the autoactivation. So as that rises, what happens is that inhibitor starts to come up. And here's the rub. This is the cool part, is that because the inhibitor has a faster diffusion coefficient than inhibitor has a faster diffusion coefficient than activator, what happens is that inhibitor, even though it's being produced, it's moving away from the scene of the crime so fast that it doesn't really achieve sufficient levels to pin down the production of activator. But what it does do is it moves out into these two wings that you see in the middle under part 3, and thus suppresses the production of activator there. And so this leads to this periodic pattern, quite a beautiful and interesting idea. So what I want to do now is I want to comment on generalizations of Turing. So in 1972, there was this important paper by Gürer and Meinhardt, and it's well worth looking at. And what you will find is that first of all, they say, well, for a two-node or two-node architecture, it doesn't have to be activator and inhibitor. You could have substrate depletion, and that would do the same thing. And then in the meantime, people have realized that Turing is a much bigger category. And I just love this paper by Michael Stumpf, and I recommend it as well. There are a number of papers of this variety recently. There's another one that involved Chao Tang and Hana El Samad and Wendell Lim, and I think the first author is Ma, where what they did, and then there's one by Tony Tsai and Jim Farrell. All of these are beautiful, doing theory, I think, the way that it should be done. And what I mean by that is that they say, well, let's not only think about the quote-unquote real biology. I'm gonna give a bit of a discussion of that later because I so object to this idea that the only biology you should look at is the real biology. I think that's misguided, and I think it's very important to look at the non-real biology, the imagined biology, because it teaches us about what's possible, and it gives us a sense of the limitations and the specific sort of Baroque features of different models. And so the paper here, done by Stumpf and company, does a comprehensive network atlas where it looks at a bunch of different architectures and asks, do they give rise to Turing? And I'll come back to that in a moment. The one by Wendell, Hanel Samad, and Chao Tang and company, that one is looking at signaling topologies and considers a whole suite of them and asks what kind of signaling motifs come out of them. And then Tony Tsai and Jim Farrell had to do with architectures that give rise to oscillations. So all of these are very interesting. So here, what they're doing is they're saying, well, look, in the upper left of the right-hand side, part A, defining network structure. My point to you would be that there are two-noded architectures that give rise to Turing instability, and there are also three-noded architectures, and there are probably many others. I'm just commenting on what they did in this particular paper. I want you to notice that in the upper left right of part C, they have exactly the two by two matrix that involves the linearization that we looked at in my last vignette on Turing, which was a bit technical, but that's quite cool. You can see that they're here up in part B, they're writing down the chemistries that show up. In other words, how would you write the chemistry of AB or ABC networks? And the point is you can tell they're using Hill functions, so we would know how to do that in a different way using thermodynamic, Langmuir with cooperativity and that kind of thing. But they're writing down the chemistry, and then to the chemistry you have to add the diffusion and put all that together. And the kind of question that they're asking is, what regions of parameter space give rise to Turing patterns? And I like the title because it says, you can achieve Turingness with a number of different network architectures, but they require you to get to specific pieces of parameter space, which is a really interesting thing to think about, both in terms of just the basic ideas about the model itself, but also in the context of evolution. One of the great questions, which I hope I will come back to later, is how does evolution search through these huge spaces? And so we'll come back to that. So now let me bring you to the paper from Sharp and Company in Science. It has to do with digits. So here you go. 5 fingers, and the question in the vertebrate limb bud, which looks kind of like a ping pong paddle, what patterns of gene expression give rise to these things, and can it be thought fruitfully as a Turing system? And so what they do in their paper, which is explained in the SI, is they try to screen to find out which genes are part of the network that give rise to this patterning, and they wanted to make sure that it's not a downstream effect. So they end up coming up with this sort of network topology that you see here that's centered by SOX9. And you can see that there's also Wnt and BMP, bone morphogenic protein. And you can look at the network setup, which is, you can see that SOX9 is repressing Wnt and BMP. BMP is activating SOX9, etc. And the claim that's being made on the right-hand side is that this will give rise to a periodic pattern. So, they did the relevant measurements. So this is, again, I'm basically surveying for you a little bit the paper from Sharp and Company, but without doing any math. I'm trying to close the loop. I'm trying to tell you, yes, all that Turing stuff that we did, if you look in their SI, what you're going to find is that it's full of the equations just like the ones that I was working with. And so that faces you with the motivation, but also the task of motivation 2 and the task of exploring these equations. So I guess I forgot to write down the equations. So actually let me see if I can do something about that. Yeah, I think I can. So, pardon me, I just need to find where I wrote this stuff down. So the equations that you'll find in their paper are shown here: 11.56, 11.57, and 11.58, which is right here. So let's just look at these. So what you're seeing is that there's basically SOX9 has a dynamics that depends on, production of SOX9 is going to depend on the presence of BMP, which will activate the Wnt, which will decrease. And let's just, take a look at that. That corresponds to this network topology that I showed you. So as I pointed out, BMP is going to activate SOX9, as you can see here. SOX9 is going to inhibit itself. SOX9 is going to reduce Wnt. Wnt's going to reduce SOX9. All that stuff is living inside of these equations. Okay, so there's 3 coupled equations, which I show you. Note that on the right-hand side here that there's a diffusion term. So that's the reaction diffusion nature. So there's diffusion. The diffusion constant for BMP is different than the diffusion constant for Wnt, which you can see right here. So there's a different diffusion coefficient. So all of that is just to say that this system of three equations gives rise to patterning of the kind that we've been talking about. And there's very deep and interesting questions about whether or not the various signals are in phase or out of phase. As you see on the right-hand side, the SOX9 is out of phase with Wnt and BMP. And those are the kinds of things that, with more time and effort, I could have gone into. And, maybe I will add a vignette about that for the, purely for the curiosity of those of you that want to think about it. I seem to have killed off the camera, so I'm almost done anyway, so let me just say that the last point I wanted to make about the Sharp and Green paper was that they they were interested in pointing out that just kind of like the dichotomization between Pasteur and the Buchners, this dichotomy between positional information and Turing is overdone, and probably there are many cases where both of them are in play at once. So you can see that on the ascending edge in this top figure, the ascending edge of one of these periodic patterns, there's positional information. In other words, the French flag playing out on only one branch of the increasing Turing concentration. So I'm not gonna belabor this any further. I think I've made my main point, which is to note that that this Turing idea is an idea whose time has come. I think it's something that, because of the discoveries about the even skipped stripes in Drosophila, that was a big disappointment in some ways, because it caused people to say, these models, they're just wrong. And but it's a powerful kind of wrongness, and it's not universal. Just because it didn't work for even skip doesn't mean that there's not Turingness out there to be had. And the only way to get to the bottom of this kind of thing is through scholarship. It's not by pursuing surprise. It's by being rigorous, and that's hard. It's not something that you do in a week. It's something that takes designing the right experiment, and then figuring out what the parameters are, and then trying to make predictions prior to the experiment being done, and then being careful about measurements and knowing about error bars and all that kind of stuff. So there's much more work to be done in these spatial patterning things. Oh boy.